Julien.
All right, okay, can you all hear me well? Fine? Good? Okay, so thanks a lot to the organizer for the opportunity to come back to this meeting. We know the story and the delays. So this talk is a bit different from the kind of normal science talk I give, so bear with me, or if you hate it, come and tell me afterwards. So, you know, this is kind of an opportunity to reflect on 10 plus 3 years and things that have changed. And so I have a kind of timeline here, which I think echoes some of what Bill was touching on in his talk yesterday. And if you look back and think at the science that we know, you know, it's sometimes said, right? It takes 50 years from idea to commercialization of technology. Well, I reckon for FEP, it's maybe more like 90 years, or maybe even more if you go back to Gibbs. But the kind of equation that we all love and work with, were formulated a long time ago, well before computer existed. But we couldn't still do any chemistry, right? Because to actually apply this idea, we had to develop all these algorithms that allow us to take advantage of computers. And it's only finally, the dawn of the 80s, around the time I was born, right, that scientists started to apply this technology to chemistry. And, Bill was talking about butane in solvent and this sort of effect. And now I would say, around about the time FEP plus from Schrödinger was marketed, is a kind of, epoch-making moment for FEP, and that's when we started to see widespread adoption of the technology. And so what is the path that we're taking here? Well, inevitably, like any good, useful technology, this will become commoditized. Everyone will want their own flavor of FEP, and more people will use it, and the people who use it will know less and less about it. So I'd like to reflect also a bit on the kind of traditional path in CompChem for taking ideas that come from academic research and convert them into tools that have industrial applicability. And the kind of traditional path in our field is we rarely see a new idea that was invented, a new method that was invented in an academic group kind of jump and be widely used in, say, pharma user. And there's a number of reasons for that. And it comes down to the focus of the different institutions. If you're an academic, right, the kind of structure in which you emerge, favor novelties. You want to be the first coming up with some clever way of doing things, or the first to simulate protein X. But what you need in terms of taking technologies and relying on them for a kind of production use in a pharma environment, what you need here is reliability, right? You need to know, can I really use this tool? Is it going to work all the time or not? Or what is the domain of applicability? And so it takes quite a bit of effort to go from something that worked once and that looked cool to something that you can rely on. And so traditionally, that job has been in our field done by software vendors. Sometimes they're spun out from academia, or sometimes they go around and they find interesting new technologies, and then they can refine it into something that you can use reliably in production settings. Now that model has worked well, but has also some limitations, and largely it's due to the asymmetry between the number of users and the number of people who can develop tools. And that kind of create a bit of a choking point. So there's not as many, there's lots of ideas here, but very few that actually become mainstream used outside of academia. Now, what has changed in the last 10 plus 3 years or so? Well, if you look around and look at the number of talks that talk about GitHub repositories and all, Well, look at this graph. The growth is the number of people using GitHub in the last 7 years or so. So let's just do a quick experiment. Can you raise your hand if you have a GitHub handle, if you ever use a repo? Right, okay. How many of you had a GitHub account 10 years ago? 10 years ago? Wow. Well, GitHub was founded in 2013, so you are really... Oh, right, Frank, of course, I know. So it's trailblazing. Okay, so this is one thing that has really changed, and I would argue is an opportunity to also think about the way we take ideas from academia and convert them into technologies that can change life outside of universities. And so largely because I guess I was around there at the time of this transition in the field, I had opportunities to interact with players outside of academia. And long story short, that led us to create an entity to help lower pain point for this interaction between academia and non-academic entities. So we created OpenBioSim as a not-for-profit organization whose goal is to be a vehicle to facilitate knowledge exchange around the tools and the techniques that we use for day-to-day research. And this is, of course, a sort of idealized view of how we would like things to work, and reality is always a bit more messy. But you want everyone here on this diagram to do the thing that they're good at, right? So if you're an academic researcher, you want to be finding some kind of new clever algorithm, research some new kind of biomolecules and how they work, what is the mode of action, and so on. And of course, we have an important role in training next generation of scientists that will go on and have careers outside of universities. Now, where is the connection here? So a lot of this research here now can generate open source software, kind of proof of concept tools that may have some utility. And what is needed to make this more easily accessible? Well, you can have an organization that is focused on good software engineering. So you decouple the problem of researching new ideas and engineering them better. And so here the key focus is working with tools that come from various sources that have been developed independently, are not meant to be compatible with each other by design, and do the work of making them talk to each other, create standard interface, and benchmark techniques so that you can start to establish what is the baseline utility. And that work can enable, in turn, people who do develop technologies who are now looking at how you can actually create value out of these tools. And so it could be the software vendor looking at creating tools that can be licensed. But increasingly also because of the direction of the field, there's more and more people in a very computational heavy pharma outfit looking at developing internally technologies so that they can create value through the platform that their company possesses. And of course, all of that is driven downstream by of course, the need to find new treatment to address unmet needs. So the key is to deliver benefits for multiple stakeholders. Helping issues from an academic perspective, a perennial problem is we can apply for a grant to do something cool. And once we've done it, we're going to actually get money to keep it running. And so many things just die when people graduate and move on. And so anything you can do to help provide maintenance and sustainability for open source software helps with our own day-to-day research. And it's about facilitating sharing knowledge to accelerate development of innovative products, and also make it more easier for people who want to maybe engage in careers in open source software engineering and supporting each other. There's a lot of open source projects that are extremely useful in my day-to-day research, and if they stop working, I will be in trouble. So anything I could do to help in turn is important. So in OpenBioSim, we have a couple of projects that we are supporting actively currently. The first one is Sire. Sire is a molecular modeling framework that was written about 18 years ago. It started as a self-funded project by Christopher Woods while he was in between jobs. And it's essentially a very flexible way to manipulate representation of biomolecules. It provides readers and writers for common molecular topologies. You can search, edit molecular system, do energy calculation, and convert data structure to from other toolkits like RDKit or OpenMM. So we use that as a kind of gateway to assemble system and then submit them to other engine where we can do interesting calculations. So what is the kind of experience of working with a tool like Sire? It would be quite familiar to anyone who uses Python. So you kind of see in the entry point, a kind of short Python script where we just download a topology file and then extract a molecule of interest. Here we use some syntax to select what we think should be a ligand, and then we just visualize it using an NGL-view integration. That's a kind of few lines of Python to allow you to do these things. Now, of course, that's not super interesting on its own, but it provides a framework for people to experiment and develop tools. And so now if you do that for a bit longer, you can start to do the kind of academic project that we're familiar with, a PhD student who spend 2-3 years trying to go from an idea to a prototype. So these are some examples of applications that were written with Sire over the years in different universities. Water swap is the Gibbs ensemble ABFE calculation methodology. It's another code that is a kind of water map, but using a different theory to do entropy of waters. Somebody here is a alchemical free energy calculation engine. Somebody was Gaetano's Calabro PhD project. This is a picture of young Gaetano. Slightly less young Gaetano is here. He's now master of Orion at OpenAI. So when about 10 plus years ago, we wrote this, and the opportunity was, we were interested in studying non-additivity or structure-activity relationship. And we were looking at the data set, and we couldn't get enough sampling to really get precise free energies to understand the experimental trend. So we wanted to take advantage of GPUs. It was kind of the new thing, but there was no open source GPU code to do free energy calculation at that point in time. So we went and wrote one so we could do the science. Now, this was kind of the right moment in time. People were looking for opportunities to develop this technology. And so years later, I became involved in a collaboration with Cresset, who used Sire as a building block to develop an FEP pipeline that's now available in Flare FEP. And so now the open source here component has become integrated as part of a solution that gives you kind of all the bells and whistles and makes the technology accessible to people who don't really want to look at Python program, who don't really like the command line interface or don't like to play with Slurm cluster, and I can understand why. But what has been interesting in the process, I would say, is by retaining an open source component in this solution, there is an opportunity to have a dialogue. And so a larger organization, like I said, is able to take this technology and benchmark it at a scale that my group could never have done because we don't have the resource and not really the focus. And so it does a number of things that I find interesting and appealing from my perspective. Well, it puts the technology in broader hands. That's always a nice feeling. But I also learn in the process about failure modes, about interesting system where we don't get good results. And for me, the negative results, I mean, of course, I want the technology to be useful, right, and work well. But actually, I'm more interested in when it doesn't work, because then I get some kind of homework, and maybe it's the beginning of a new project. And so being able to have this dialogue and have knowledge about how the tool works coming back to you is very, very useful to drive your own academic research. Right, another project that we work on is BioSimSpace. And think of BioSimSpace as a framework to enable interoperability between different biomolecular modeling package. So this started, it's been on development since 2017. This started as an EPSRC-funded project led by CCP BioSim that supported two scientists, Lester Edge and then Tony May, to work on this for a few years. The idea was to make it easier for different academic groups to share their technology. Eventually, like everything, the funding ran out. But by then, we had gained some traction. People thought this could be quite useful in a non-academic context. And so eventually, through OpenBioSim, we were able to keep Lester working on this project. So what do you do with BioSimSpace? So it's a Python code base that abstracts common simulation tasks, things like parameterizing molecules, putting together systems. It uses Sire as a backend, but it does more than just doing translation of file format. It tries to capture programmatically all the knowledge that you would have in a lab that allow you to use effectively a tool. And then it allows you to run in an interoperable manner different simulation engine. So what I would say, one thing, if you work with a diverse ecosystem of tools that were developed independently, one of the big challenges is making them work together. And so half of the job of BioSimSpace is creating a single environment where all these tools can be distributed, so that you don't have to have headaches with Comba if you get BioSimSpace. So that removes some barriers and help people start using the tools. So then you need some interoperability layer here that allow you to take input and output from different tools and then pass it between themselves. But you need more than that. You also need to capture in the framework best practice for using the different tools and then expose that in a standard way via Python so that user can interact with the framework. So how then would that look like in a few lines of code? This is an example of a script that would allow you to specify how to do an energy minimization. And that's done in a very generic way where we just specify here, we let read some input file. Behind the scene, we work out what kind of file format this is. Let's specify just very few keywords, and we want to do some minimization. If you know what you're doing, you can, of course, go and edit this. But if you just want a very simple syntax, it's also possible. We set up a protocol, a process that allows to perform an operation on the system. We don't actually specify what MD engine is used for this. We work out what's available to do this, and then just export the output, right? So that's just a few lines of code here. You can turn this script into what we call nodes, which is basically a way of specifying what the input and the output are. So the script we had on the previous slide is here. Now we have some boilerplate code here. And what it does is that then it allows to take this code, export it, and reuse it as it is in different environments. So you could run it interactively in a notebook, and that's usually how you could put together the script to begin with. When you're happy with it, you can export it, run it from the command line, or you could execute it from another script, or export it as to put it in various workflow engine using, for instance, common workflow language wrapper. So what this kind of technology allows then is it enables people to interact with the broad open source ecosystem and pick things that they like and then combine them together. And so one of the job we do is we help developers come up with their own pipelines by combining different components. So there's a good open source software out there. You don't necessarily want to go and reinvent the wheel. And if you facilitate making that component talk to other things that you may have in-house that are more like kind of your secret sauce, then you can accelerate product development. So this is summary of a pipeline that Exscientia has put together with the help of BioSimSpace that combine different academic and open source components with protocols that were developed in-house. Now, the same framework is also useful for academic research, the kind of traditional project for PhD students and so on. So perhaps some of you have seen the poster of Anna and Finlay yesterday. So Anna works on interoperable FEP pipelines, and I'll say more about that in a minute on the next slide. But the idea is that a lot of what we do is essentially the same thing. When you build an FEP pipeline, many pipelines, you set things up, you run them, you analyze them, right? And this keeps being re-implemented around specific solutions. But it's not that easy to modularize that. There's a lot of dependency on the setup, simulation, analysis stage that from a developer perspective, we would like to understand better, and I'll give you an example on the next slide. Finlay works on ABFE pipelines. He's looking, for instance, at different ways of automating ABFE calculation. For instance, one study we've done is to look at different kind of framework you can use to implement restraint in this calculation. And so we can do the science, test different methodology, compare them. And when all that's said and done, the kind of best results that emerge then can be implemented in the framework by a software engineer working closely with the people who did the work in the lab. Now, because all of that happened in open source code, in an open environment, these projects have been sponsored by different pharma partners. But these projects have also attracted contribution from other companies because for a number of reasons, this is also on their development roadmap. And so it makes sense tactically to, at some point, to say, okay, maybe we should join forces here. And to give you an example, like ScienceCheck contributed support for PMEMD in this project, so that was on our roadmap. But because somebody else was committed to work on it and to join forces with us, we all save time in the process. Right. So what do we aim to do by having an environment with all these tools together? So hopefully we can start to benchmark better methodologies. And going back to the idea of these RBFE pipelines, this is an example of an experiment we've been doing where we specify what this is about trying to benchmark hydrogen mass repartitioning protocols. So as all of you probably know, this is a cool technique that you can use to increase integration time step by playing a bit with atomic masses in your system and hopefully make your simulation run twice as fast as you would be able to do otherwise. So we define a protocol in BioSimSpace that behind the scene depend on a whole bunch of different tools. And the key is that protocol is fixed here. And we pass our setup system to a simulation engine, and then we analyze the results. Here we have standardized the analysis. And the experiment we're doing is to change the simulation engine. And we're looking for a given protocol. What is the performance of the engine? You can see here results in detail for TIC2. What you kind of take a message from looking at these plots. We're reasonably happy with SAMD or Amber here in terms of performance. They're basically virtually the same, which means that they're able to deal with the protocol, and there's little difference in the engine. If you look a bit closely, you would probably notice that the PMEMD results are a bit more precise than the SAMD results for the same protocol. So that's telling us maybe there's something about the way the engine does mapping that translates into better efficiency. That's something we could be looking at next. If we look at GROMACS, and I hesitated a bit to put this on the slide, I confess. So you can see, obviously, things haven't gone very well in this particular experiment, right? Fundamentally, there's no reason why this engine would be worse than the other two. So this is telling us that the way we are implementing hydrogen mass repartitioning just doesn't work very well. in that pipeline. So there is more work to be done to implement something that supports robustly GROMACS here. But this tells us then we can go back to the setup and look more carefully at what decision are we making that allow us to run HMR smoothly in this system, but not in that case. And then we can start to ask from a developer perspective, interesting question about maybe differences in the way integrators vary between these different codes or the way constraints are made. No, same for, right, so that's FF14 for protein, TIP3P, SAGE, 2 for the ligand. Another thing we saw initially is this kind of out-of-the-box result. Looking at all the edge that we had running on network, there was, for some of the system that we looked at, pretty high failure rate initially. And by failure rate, I mean jobs where at some point one of the lambda window blew up for some reason. And we looked at this more closely. And for each of these engines, we found different reasons for the failures. So in the case of SOMD, for instance, we realized that the jobs that were failing here were due to suboptimal mapping that had been produced by the setup protocol. So we could go back, tweak this, improve the atom mapping procedure, and then repeat this and basically remove all the failure rates. The case of PMEMD, we were able to deal with that. I'll show you how on the next slide. Yes, I need to finish, right? Almost there. So we ran this pipeline, and we saw issues. We were able to address some of the issues for the code we knew the best. For the other, because we were also in contact with people also using this tool in slightly different pipelines, we could start to reach out and have discussion. We're seeing this kind of failure rate when we're running PMEMD in our pipeline. Do you see that as well? And William had a poster on some of the RBFE pipeline that Excellence has put together. And so through this discussion, we were able to identify differences in the protocol we use to equilibrate our input. And then adopting the procedures that had been used by the other team at Excellence, we were then able to address our failure rate with PMEMD. And so through this discussion, we can collectively identify, share best practice, and then capture that in a framework. Okay, and so just to wrap up then, what I hope is that an organization like OpenBioSim may be a way to help people develop innovative tools that leverage the open source software infrastructure in a way where every party can benefit from the increased connectivity. And let me just acknowledge, well, first and foremost, all the people who, and many of you in the room here, are open source developers who, basically share the fruit of your hard work freely so that people can build on it. And then the various people in academia and industry that have been supporting this project. Thank you.
So please, yes.
Hi. So as someone who started off in academia working on engine engines, then went to working for a software vendor but now is a industry consuming the same software. The appeal for interoperability, I think, is oftentimes questionable in industry in terms of like what we tend to want is to have a method that is robust across a large amount of chemical space and that doesn't fail. Oftentimes when things are interoperable, that just builds up a Cartesian protocol for different ways for things to actually fail in practice. I mean, I think we've seen just how difficult it can be to even get Amber, GROMACS, OpenMM to all be self-consistent. Have you guys more thoughts on how to actually control the failure modes of everything fully?
Yeah, so obviously we've got different, we're sitting on different places here, but so if your pipeline is interoperable and something new comes in, you can swap it in and use it and test it. And maybe today you really like to run your calculation with engine X, and then there's a new update in engine Y. And if you don't have to redo your entire stack, to be able to roll out engine-wide, that's a win. In terms of also science, if you come up with a very super cool, clever method, but it's only available in the world of people who understand the language on how to create your input for engine X, then your audience is much smaller. And so in terms of sharing tools and helping disseminate ideas at the maybe earlier stage, right, when we're still testing our new technologies, I think this will help accelerate progress. Now, once maybe you have something quite robust, and you don't really foresee the need to change it because maybe it's as good as it can be. Maybe interoperability is less important at this point.
All right, let's thank Julien again.
I need HDMI.
Yes, I don't have this here.
That guy, yeah, I need the old-fashioned one.
Are you happy to record it?
Yes, sure. That was easy.